I was given the talk, the HTCondor Philosophy, but I don't really want to talk just about the HTCondor Philosophy alone today. Really what I want to talk about is the High Throughput Philosophy, which kind of undergirds a lot of what we do with HTCondor. So to get in the mindset of this, let's imagine a world where HTCondor doesn't exist. There's no code, there's no sched-d, there's no start-d. And in such a world, I want to ask you, are these high throughput ideas that we do still valid? And of course, we think they are. And at least I find this a very helpful technique for when we decide to add things to Condor or to remove things, to think not just in terms of, well, is this easy to do in the code that we have today or the daemons or the services that we have, but is this valid in the greater scheme of high throughput? If we didn't have Condor, would these ideas still be valid? And when we do this, again, we don't start with Condor. We try not to start with technology, but we start with people, because people have problems. So here's an example of a person with a problem. Here's Joe the chemist, or Joe the chemist, and I would try to explain to you what kind of computational problem she might have. But I think our keynote speaker, Dave O'Connor, this morning gave us a great example of the kind of computational problems that modern science and genomics is really driving a lot of the high throughput solutions that we have. But before we get into sort of the high throughput philosophy, there's sort of some lemmas that I want to start with that we sort of take for granted. And I think Christine will be talking about this a little later, but we will take as given that these three things, that the total amount of work that you have can be broken up into smaller independent jobs, that we only use files for communication. We don't need real-time communication between these units of work that we break up. And our goal is to optimize the time to finish. We're not trying to polish screws and make each particular job go fast, but we really want to know, we really want to get to that last job. We're concerned about the long tail of these jobs. So with that, we think that this unit of work, the job, has the job nature. And then we think a lot about what a job is. And some aspects of jobs, their jobs have identity. They each have a unique number that identifies them. They have a complete description of them that the user gives them that's outside of the job in a submit file or something like JSON or something that completely describes that job. That given that submit file, given that description, we know everything there is to know about the job. That description may have pointers like files or other things, but you can completely describe a job in a small nature. Jobs also have a life cycle. So they're given an input sandbox, they run for a fixed amount of time, and they produce an output. Now this life cycle may be interrupted, and may be restarted, may be rerun, but jobs have kind of a particular life cycle here. And this is, I think, a big difference between the high throughput philosophy that we see in Condor and maybe other batch systems, and systems like Kubernetes, which don't often have the job nature, but are designed to run services. So they don't have the job nature. These services run forever. They don't necessarily have any output. So this is sort of what we're talking about, the job nature, and we want to be able to process things with the job nature. So given that you have this work, you follow this lemma, you have a lot of jobs that you want to complete, what's the first thing that you need? And again, imagine a world without Condor. So the first thing you'd need is an access point, which is just a place for your stuff or a place for your job. And the access point keeps track of work to be done. It keeps track of work that has been done. It maybe knows about the order to do the work. It is responsible for managing all of your jobs. Now, when we talk about this in a world outside of Condor, you may think, oh, I'm going to have some skeuomorphic interface. That's I'm going to talk about a desk and files and pieces of paper, but no. An access point is a computer. Maybe it's a laptop, maybe it's a desktop, maybe it's a server in the cloud. So we think about an access point and the things it needs to do. And let's say we didn't have Condor, we might implement an access point as a spreadsheet. And it has attributes, one row per job, and it has some things about each job. And kind of an interesting thing on the right here is this beaker number, because these jobs have attributes that maybe aren't generic to Condor, that maybe are specific to a particular user. So an important point on these jobs or access points of jobs, we have to be able to have an extensible schema, so we can record information, not just that every particular batch job knows about, but only that are important to particular jobs. So principles of this access point are that it's robust. It doesn't necessarily never crash. If we could figure out how to write code or build machines that never crash, that would be worth a paper or two right there. But what we can do is we can make it robust so that after a machine or after the software does crash, we can recover. Another important point about these access points is that they're yours, that you control it. They represent your needs. They may be shared. The cardinality may be funny. You may have more than one access point, but you control your jobs and your access points. Because we break up work into a lot of different jobs, they need to be scalable. And the access point owns the job policy, and it makes all the decisions. It may not implement the decision. It may delegate decisions about when to remove jobs, when to start jobs over again, but it is responsible for owning that policy. So we're imagining a world without Condor. Let's imagine a world with Condor now and talk a little bit about how Condor implements an access point. Basically, as Todd said, an access point means a SCED. So if you run a PS, you'll see it's running this Condor SCED process. And we in Condor are very fond believers in the Unix way. So we have lots of processes. We believe that creating a process per service with very well-known failure semantics that we can kill and restart, and each cleans up all of its memory on exit, is the right way to build robust services. And we take, in the Condor philosophy, we take very clear care to know and to delineate and to talk about what the responsibility of each service is. And we're very clear on this, and this is an important part of the Condor philosophy. And we may have many services per machine. In particular, the access point isn't just a SCED, but it also forks and execs a running shadow process for each running job. So on an access point, we have not just a SCED, but a bunch of Condor shadow processes running under it. Now, you may think that that's kind of expensive to have a process per job, and it is a little expensive, but it's worth it because it obeys this philosophy that we're very concerned about robustness. We're much more concerned about robustness than absolute performance. We can get scalability in other ways, but we're very concerned that we have this process level architecture with one shadow running per user. And the shadow is responsible specifically for the jobs policy when the job is running. So it is expensive to do this, but we can scale by adding many access points. So if we run out of processing power to do any particular one thing, we can add access points, maybe on different machines, maybe on the same machines. And this allows users to be able to submit near where their data is. So if they have one of these fancy genetic sequencing machines that we heard about this morning, maybe the submit machine is right near that, so we don't have to schlep our data all the way across campus to just be able to submit jobs. And this yields to another important part of our philosophy, that is submit locally, run globally. So we want to move the access points closer to the user. And once the access point has the work, it can send it to wherever it needs. So it's not just the SCED in the shadow, but robustness requires a parent. We want to make sure that these jobs stay running, and should they crash, something else restarts it. And that is the Condor master. And a Condor master runs on every machine that runs Condor. If a machine at all has Condor on it, it's going to run a Condor master process, which is a lot like init, which apparently is spelled differently now. And it's responsible for starting, restarting, handling the Condor on and off commands. And it kills processes that it detects are not running properly. And again, this is another way that we get robustness, is that we positively and affirmatively try to detect if a child is still not just running in the Unix sense, but processing and giving us keep alive signals. And if it doesn't, the master will kill it and restart it. So this idea of management that the master does when it manages the SCED or processes under it is very keen also to Condor. The master manages processes. And in Condor, we're very big on this word manage, and we use it in a number of contexts. And we think it's very important to building distributed systems. And we have very specific things we mean by manage. When we manage things, we want to manage all the things. Manage doesn't just mean create processes, but it means to remove processes. And then not just the processes we created directly, but what they created, and to clean up after them. And in a lot of ways, this being able to clean up processes and their detritus is a lot harder and a lot more work than creating them in the first place, especially when you're distributed. Management also means that we need to measure and report about what we create. So if we're using too many resources, or maybe not enough, that any management process like the master or like the SCED can report and do reporting on all the things that it has created. And because any system can be overloaded, management also means being able to put limits on everything that we do create. There's limits in the SCED that limit how many processes it can create, how many jobs it can run, how much bandwidth it can use, how much disk space it can use. Everything that we should be able to manage, Condor, it can be able to manage, Condor should manage. And I think this is maybe one area where the implementation is sort of behind the philosophy. In principle, there's almost an unlimited number of things that we could want to limit, but that are sort of difficult to do or we haven't got around to yet. But the base philosophy is that no user, by using Condor, should be able to overload any machine on the network, and that Condor, or the distributed high throughput system, should be able to do that limiting. So given that we have this access point, can we run on it? Well, yes. So theoretically, we should be able to run our distributed high throughput on even just one machine. But that one machine may not have enough power, and it may be shared, and we should be a good citizen. So we want to run on every possible machine. And again, this is an important part of our philosophy, that we want to run on as many machines as possible. But because we want to run on as many machines as possible, there's something funny here, as Matthew West sort of alluded to in his question, thank you. Machines are different. Maybe some are ARM, maybe some are x86. Even if they're all x86, maybe some have more memory or less memory, or are behind a firewall. And so we need to be able to manage places where we can run jobs that aren't the access points. And we call these execution points, or maybe worker nodes. And as such, they need to advertise what they have. Because they're all different, they need to be able to say, oh, I'm an ARM, or I'm an x86, or I've got a terabyte of memory, or I have lots of disk. And again, this must be extensible, just like the jobs are extensible, because there may be some user-specific or site-specific attributes that they need to be able to say. And the job itself may be a guest on these execution points. So it's really important that we clean up and go away on a moment's notice. And this is all the responsibility of the Condor startd. The startd, by definition, defines an execution point, and it represents the policy of the machine. It creates Condor slots, which are places for jobs to run. And these slots can have policy of themselves. So you may ask, well, we know the jobs have policy. We know the startd has policy. What if these two policies don't match? What if they conflict? What if they started working and now they're different? Who wins? Well, a very important part of the way we think about the world is, the machine always has the opportunity to win when there's a conflict in policy. The job is always a guest. So the startd's mission statement is really kind of nearsighted. It doesn't really see the rest of the pool or all the jobs or other machines. When the startd makes decisions, it only has three inputs: itself, any job that is already running, and perhaps one candidate running job that may preempt it. And it knows nothing about the rest of the system. So the things the startd can do, it says, well, I can only run some kind of jobs, like I can only run chemistry jobs. Or it can preempt jobs. It can say, well, I'm happy to run jobs from anywhere in campus, but by gum, if a chemistry job comes in, I'm going to kick off any other job because I like the chemistry jobs. It can only run one job of some type. So you could say, well, I know that these database jobs are very heavy on my disk. So once I see one, I'm not going to run anything else. So it can do all these things. But of all the things the startd on the access point does do, it does not actually run the job. Just like the SCED spawns a shadow to help run the job, the startd spawns a starter to run the job. So the idea here is that the startd manages the machine, but the starter manages the job. So there's one starter per job and thus one per slot. The responsibilities here are that the starter manages run the job on the machine. It manages cleaning up. It creates our universe metaphor, like Docker universe or Java universe or vanilla universe. And again, it cleans up after the job because we're kind of like an Airbnb visitor on the machine. The starter also implements file transfer, and this is a very big part in Condor. So Condor can get the sandboxes to and from the access point to the execution point via explicit file transfer or via shared file system. And in general, we really prefer explicit file transfer. Why? Well, because it's managed. We can limit the number of concurrent file transfers. We know the size. We can measure the amount of data. We can measure the network impact. But when all this happens with a shared file system, that's via a third party that's often not managed. I don't know if anyone's crashed an NFS server lately, but the reason we crash NFS servers when they're overloaded is because there's no management. When you ask for a request, when you request a file on NFS, NFS just has to give it to you. It can't say, I'm overloaded, please try again later. And that's something that the Condor access point and the Condor file transfer can do.
Greg, let me interject here that it's also a handling of errors. If the biggest challenge we face is failing to get access to files when the job is running.
Yes. And of course, error handling is a big part of management. And so this leads to kind of the two-faced nature of Condor. Condor, or high throughput computing in general, there's always a split responsibility. There's the access point side, which is responsible for the jobs, and there's the execution point side, which is responsible for the machines. And we encourage having different configurations or different policies on both sides, because this stems from the inherent distributed nature. There are responsibilities of the job and the access points, and there are different responsibilities that an execution point have. And we don't try to unify these because we believe they're fundamentally coming from different areas of responsibility. So an overview of Condor then is we have these three sides. We have the access point, the execution point, and a central manager in the middle, which we haven't talked about yet. So moving on to the central manager, this is the one part that is the, the central point. There's only one of these in a pool, and it sort of defines the pool. A pool may have one or more access points. It may have one or more execution points, but a Condor pool always has exactly one central manager. And the central manager is composed of two parts: the collector, which is a central database, but this is an in-memory database, and everything reports to it. So if it crashes, it loses everything. So our protocol is always to be updating. And because of this, it's not a central point of failure. So if it goes down, we lose the state, but everyone is sending updates to this, so it always comes back. And this gives us kind of an implicit garbage collection.
Sorry, Greg, you're down to your last couple of minutes.
Yep. So the final piece is the negotiator, which is the other half of scheduling. And it's slow, it's deliberate, and its responsibility is to allocate machines to users. So we have this kind of two-phase scheduling in Condor. The first phase is what the negotiator does, where it decides to divide up the pool to different users based on a number of things: priority, fair share. But then the second phase is done at the access point in the SCED, which decides, given that a certain user has gotten 5 slots, the SCED will assign those slots to particular jobs. And because of this, there's not a single point of failure. So finally, what I want to talk about is we talked about high throughput computing. You'll hear a lot of talk now about distributed high throughput computing. A lot of this is just taking these same ideas and going meta. So if we have 2 pools, we want to be able to send jobs from one pool to another and run not just in one cluster or in one campus or across campuses. And this destination may not necessarily be a Condor pool itself. So I'd like to thank you all for listening to me, because we said, remember, people have problems. Maybe the people in this audience are lovely Condor users, have problems, but people also solve problems. So I want to thank all of you who have either solved problems that we have created, or maybe you've given us problems that hopefully we've been able to solve for you. So with that, that's the end of my talk. I don't know if we have time for questions, but I have a office hour later in the week that I'd be happy to talk to anyone on any subject.